Let's continue our discussion about automata or theory of computation. On our last video lecture, we discussed the history of theory of computation, and we also reviewed some terms, some concepts from discrete mathematics and in artificial intelligence. And we also defined some terminologies that we're going to use in theory of computation. So for this video lecture, we're going to discuss some terms that we're going to use every now and then. So let's start with these four terms: symbols, alphabet, string, language. So if we say symbol, these are characters that represents the input of the machine, and it is considered as the smallest building block in the theory of computation. Okay, and it could be a letter, a number, or even a pictogram. So for example, so symbol could be 0, 1, 2 or ABC. And again, it represents the input for a certain machine. And the collection of symbols to define this is the only input accepted by the machine, we call it alphabets. Okay? And we use sigma to represent the input, the collection of input for a machine. Okay? So for example, the collection could be AB or DEGH. Okay? So while strings and words, these are sequence of symbols defined in the alphabet. Okay? So for example, our sigma contains AB. So our string could be from this alphabet. So we could have a length of 1 that contains A or length of 1 that contains B. Another example, length of 2, which contains AA, or length of 2, which contains AB, or even length of 3, which contains AAA. Okay, so length defines the number of symbols in a string or words. Okay, so let's have an example. So how many strings of length of 2 are possible over alphabet AB? So we have two possible values AB. So 2 raised to 2, we have 4. So based on the power of 2 rule. So which are AA, AB, BA, and BB. And let's answer this question. How many strings of length 2 and starting with A are possible over alphabet? So it is related to the first bullet, first question. So we're just going to consider a string that starts with A. So how many? Based on this, we have 2, AA and AB. Okay, so let's continue. How many strings of length n are possible over alphabet A, B? So again, using power of 2 rule, the formula will be 2 raised to n, wherein n is the length. Okay, and in case we have more than 2, like in this example, A, B, C, D, the formula will be the number of symbols in an alphabet raised to n. Okay, so this will be our solution. This will be our equation to determine the number of possibilities on the given length, given alphabet. Okay, let's continue in defining language. If say language, this is a collection of strings and words which are accepted by the automaton or by the machine rather. Okay, and it could be finite or infinite. It depends on the rules in defining the string. So for example, so we have sigma contains AB. So language 1. So we use L1 or subscript to define What language? So language 1 equal to set of all strings of 2. So we define the string length. So based on this, we have 4 possible strings. So therefore, since we could count the number of strings, it is finite. So it's a finite set, it's a finite language. Another example, another language. So set of all strings of length 3. Again, same as with the first example, we have a specific length. Okay, so combination of A, B to form length of 3. So how many? We have 8 possibilities. Since we can count, therefore, the string is finite. So this language is finite language or finite set. But how about this example? Language 3, set of all strings where each string starts with an A. So how about the length? You don't have a specific length. So therefore, so it could have 1A, 2As, etc., etc. So we cannot count the number of strings based on this rule. So therefore, this is an infinite set or infinite language since the length is not defined. Okay. Now, let's discuss what is power of sigma. So basically, power of sigma defines the length of the string. Okay. So sigma raised to n, wherein n is the length of the string. So for example, we have sigma 0 raised to 0. It means the length is equal to 0. Okay, so empty string. So if you're referring to sigma raised to 1, okay, so length of 1. So we have two alphabets. Okay, and for sigma raised to 2, so length of 2, so we have 4 possible values. Okay, for sigma raised to 3, length of 3, so we have 8 possibilities. Okay, so how about sigma asterisk? Asterisk means it's a wild card. It could be either 0, 1, 2, up to, or any value, any positive integer. Okay, so it means the string length is variable. Okay, so the length could be any. Okay, we're referring to all lengths. And also, it represents the infinite set since the length is not defined. Okay, and also it could represent the parent of all languages. Okay, so we could decompose sigma asterisk as equal to sigma 0 union with sigma 1 union with sigma 2 union with up to sigma n. Okay, so for example, so epsilon, AB, AAB, etc., etc. So based on this example, we could say that language 1 is a subset of sigma asterisk, language 2 is a subset of sigma asterisk, and language 3 is a subset of sigma asterisk. Okay, so that's the end of my video lecture. See you on the next video. Thank you for listening.